Okay, so welcome to topic 6, so light and chemical detective. This is our last topic for biological and physical chemistry, and as you know, my name's Stephanie, and these are not a replacement for attending the lecture, they're just there as extra revision material or source for you. Okay, so the objectives. So what we want to cover today and get you to understand by the end of this video is hopefully understand the basic features of molecular orbital theory and how it explains bonding of certain compounds, be able to draw molecular orbital diagrams. Okay, so this is for the first or second period, and you'll be given the fill template that you'll need for that, so you just need to understand how to fill in the templates for the particular compounds. Be able to determine the bond order and correlate this with experimental data on bond lengths and also magnetism, so paramagnetism and diamagnetism. So be aware of the key areas of the EMR spectrum and which key areas are used for analysis of organic chemistry, so the structural determination. We also want you to understand how the EMR interacts with the matter in these areas. So be able to correlate the technique to the relationship with the wavelength. Also be able to solve problems using Beer's law, so calculate concentration or percent transmittance. And the equation you need again is in your extra sheet for that. We also want you to be able to understand IR spectrum and be able to correlate particular compounds to particular spectrum based on those key functional groups. And again, in your exam, you're going to be given the supplementary, which will give you that correlation table. Okay, so let's firstly start with molecular orbital theory. So molecular orbital theory carries on from your valence bond theory and hybridization. So back in Chemistry for Living Systems, we talked about valence bond theory and hybridization. So remember, hybridization is a way of the orbitals to arrange themselves so that we can get equal bonds. So for example, with methane, it makes 4 bonds to the hydrogen atoms from the central carbon, and we have an sp3 hybridization. Okay, so valence bond theory also accounts for your geometry of your molecules. Okay, so what shape we end up with. So the aspects that were very poor in valence bond theory can now be explained using molecular orbital theory. So remember back to quantum numbers. So we use Schrodinger's equation, so the wave functions to describe our atomic orbitals. So I've just put them in here for you as a reminder. Okay, so our quantum numbers, so principal quantum number, angular momentum quantum number, magnetic quantum number, and magnetic spin quantum number. And we used, so this was our size and energy, our shape, our orientation, and our spin. Okay, so molecular orbitals are carrying on from this. So there's some characteristics that are the same between your atomic orbitals and your molecular orbitals. So we know that we can have a maximum of 2 electrons with opposite spins. There's a definite energy for each of the orbitals, and same principles with electron density. Okay, so it's a contour representation. But our molecular orbitals, the difference is it's the entire molecule and not just the one atom. Okay, and chapter 9.7, 9.8 specifically covers this. Okay, so the hydrogen molecule. So let's start with the hydrogen molecule because it is our simplest molecule, and we've got 2 atoms that are coming in together and making a single bond. So if we have a look here, we have our hydrogen atomic orbitals. So 1 electron's in the 1s shell. They come together and we get what we have here is constructive interference, and it's got a lower energy than our original atomic orbitals, and this is called our bonding molecular orbitals, and they're very stable because they're lower in energy. So we also, when we have the combination of those 2 atomic orbitals, we have what we call destructive interference, and this leads to a higher energy. So looking at our energy chart, it's higher than the original 1s, and it's therefore less stable because it's a higher energy. and we call this the anti-bonding molecular orbitals. And we have a nodal plane between the nuclei, so there's no electrons in between these, whereas this one we have a high concentration of electron density between the two electrons. Okay, so let's have a look at some diagrams with H2 and helium-2. So H2, you have your two hydrogen atoms. Okay, they come together and we make a bonding and an anti-bonding orbital. So we have constructive and destructive combinations. The electron, okay, goes into the lowest energy and then you fill it up. So this one has 2, so it's going to go 2 into the bonding, and it's going to make a nice stable molecule because it's got a lower energy than the original 1s orbitals. If we look at helium, each have 2, so in total we're going to be filling 4 into our system. So starting from the bottom and working your way up, so we've got 2 here and then 2 go into the top. So looking at our energy, you can see this is lower in energy, but this is a lot higher in energy. And what we know is that helium-2 does not exist as an unstable molecule. And molecular orbital theory really helps to explain this. So if you're looking here, we've got a low energy, so we've got a stable sigma bond, and then we've got this anti-bonding that's destabilizing that bond. So generally, if the number of anti-bonding electrons is the same as the bonding electrons, it's an unstable molecule. Okay, if you've got a fewer anti-bonding than you have bonding, then it would be stable. And we'll see on the next slide how to mathematically work that out. Okay, so we can see here, so helium-2 doesn't exist and H2 does exist. And this ties into bond order. So bond order is used to work out the stability of a covalent bond. So the formula for bond order, which is not in your sheet, is half the number of bonding electrons minus the number of anti-bonding electrons. Okay, so if you get a bond order of 1, it's a single, 2, it's a double, 3, it's a triple. Okay, if you get a 0, it means there's no bond. Okay, you can have fractional bond orders, they're not always a whole number, and the greater the bond order, the shorter the bond. So that comes back to your understanding of bonds. So single bonds are the longest, double and triple are shorter as you go along. Okay, so let's have a look back at our 2 examples. So we've got helium-2, and hydrogen-2. Okay, so if we do our bond order formula, okay, so for H2 we've got 2 bonding and 0 anti-bonding, so it's half 2 minus 0, which gives us 1. Okay, so it's a single bond between those two. So let's look at helium. So we've got half 2 minus 2, which gives us 0. So this does not exist. It's an unstable molecule. Okay, so that's our first period. Let's look at our second period. They're a little bit more difficult when we get to our second period, but the principle is kind of the same. So the molecular orbital is the sum of the total number of electrons in the atomic orbitals combined. So same again. So the atomic orbitals combine most effectively with atomic orbitals of similar energies. Okay, and when the atomic orbitals combine, their energy is proportional, or the effectiveness of that combination is proportional to their overlap. So the more overlap, the more stable; the less overlap, the less stable. So the molecular orbital can accommodate 2 electrons with paired spins. Okay, and the way we fill it, remember, is our Hund's rule. So we put 1 electron in each and then we double up. So let's look at some examples. So let's look at lithium. So that's our first one in the second period. So we've got our 1s2, 2s1. Okay, so we've got 3 electrons in each of our s's. So we've got 3. So putting them together, we go 2, 4, and then we've got 2 left, so it goes in there. So 2, 4, 6. Okay, let's look at beryllium. Okay, so now we've got an extra, we've got a 1s2, 2s2, so filling that up, we've got 2, 4, 6, 8. Okay, so let's look at our molecular orbitals, the bond order, to see if these are stable. Okay, so this one would be a half, it would be 4 bonding and 2 anti-bonding, so it would be 1 single bond. This one here, we do a half, we've got 2, 4, 2, 4, so it would be 4 minus 4, which gives us 0. So this one wouldn't exist, the E2 wouldn't exist. Okay, so when we go over to the next section, we're introducing our p block. So remember, your p orbitals are your set of 3 degenerate x, y, z. Okay, so when we talk about the molecular orbitals of these ones, we have our bonding, so we have an increased density between the 2 nuclei, and we've got our anti-bonding, so we've got that nodal point. So we've got our Z, okay? We've got our Z, and then we've got our X, okay, and then our Y, so on those different axes. So what we actually can see is, because of the types of overlap that we get, you have your 2pZ having a lower energy than your 2px and 2py. So 2px and 2py are of a similar energy, okay, but this one is lower. So putting that in, we've got our lower energy, so that's our 2bZ, and 2px, 2py is this one, and then we have our anti-bonding that correlate to it. Okay, so that's not too complicated, but some of these are different. So if we have a strong interaction between our 2s and our 2p, we actually get a change in our splitting interactions. So this is what we know. This is our general kind of one, and that's when there's not much interaction between that 2s, 2p region within the molecule. But if we have a high interaction, then we'll get a different split. So we actually have our 2p energy, our bonding going up, okay, on that middle plane, so that center sigma bond, and then our pi bonding ones stay in the same energy, okay, but our S drops even further. Okay, so we have a big split between them. And the atoms that do that, so O2, F2, Ne2, so towards the right hand side of our periodic table in that P block, we have not much interaction between them, our 2s and our 2p's, but over towards the center kind of region, so our boron, carbon, nitrogen, we have quite large interactions, so we have a change in that split. Okay, so if we have a look at this slide here, it goes into our 2s, 2p interaction. So look at our examples here. We've got our boron, carbon, nitrogen that have that large interaction. So remember, our 2p degenerate set is lower than our one that's our sigma bond. So our pi bonds lower in energy than our sigma, but then if we have a really small interaction between our S and our P's, then our sigma is lower and our pi bonds are higher. Okay, so looking at our anti-bonding, they're not changing. So filling these 2, 4, 6, okay, 2, 4, 6, 8, because we're increasing 2 electrons each time, 2, 4, 6, 8, 10, okay, you can see the picture here, so 2, 4, 6, 8, 10, 1, 2 for the next one, 2, 4, 6, 8, 10, 12, 14, okay, and then for the next two, because we've added those two, the next two would be in here, okay, so you can see that we have paramagnetism on a couple of these, and the rest are diamagnetic. So remember, paramagnetic means there's unpaired electrons, whereas diamagnetic means there's no unpaired electrons. So our boron has unpaired and our oxygen has unpaired, whereas the rest of them don't have unpaired electrons. Okay, so when we look at oxygen, this is kind of like our classic kind of case here. The Lewis diagram shows you this. Okay, so we've got a double bond and we've got two lone pairs on each oxygen. But experimental data shows that oxygen acts like it has two unpaired electrons and it's paramagnetic. Okay? The Lewis diagram fails to predict the unpaired electrons, but the molecular orbital theory can predict this and the bond length. So we know that this is paramagnetic and we can see these two unpaired electrons here. And we know that the bond length is kind of a bit more than a double bond. And we can see here that our bond length is 121. Okay, so that's showing you that it's a little bit more than a double bond, and it has a number 2 bond order. Okay, so that's pretty much what we've just talked about on the other slide. So molecular orbital theory is really good for showing paramagnetism and diamagnetism. Okay. So let's have a look at molecules where we have a heteronuclear diatomic molecule. So heteronuclear, two different atoms that are combining to make that diatomic molecule. Okay, so the classic case is nitric oxide. So it's a molecule that's used in metabolism, and you'll talk a lot more about nitric oxide as you go through your degree. So it's an important molecule in the body and it's a gaseous signaling molecule. So it's quite reactive and it's highly regulated. So there's 11 valence electrons and 2 possible Lewis structures. So our 2 possible Lewis structures is with a free electron on the nitrogen or a free electron on the oxygen. Okay, and the bond length is measured at 115, which is close to that of a triple bond than of a double bond that's indicated here. So if we do let's have a look at the molecular orbitals. Okay, so we've got our nitrogen, okay, we've got 2s2, 2p3, and our oxygen is 2s2, 2p4. Okay, and you can see the energy diagram here. So our oxygen atom has lower energy than our nitrogen atom. And when we combine the molecular orbitals, we get our bonding and anti-bonding 2s. We've got our bonding and our anti-bonding 2p's. So filling them up, we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so we get 1 unpaired. Okay, so you can see that the combination of these results. So normally when we have the combination of these atomic orbitals, the less electronegative atom is slightly higher in energy. So in this case it's our nitrogen one. When the molecular orbitals are mixed, the greater contribution comes from the atomic orbitals that's closer in energy. So the one that's closer in energy out of nitrogen and oxygen is actually the oxygen. Okay, so the oxygen bonding orbitals are closer than the nitrogen. Okay, so the bonding ones. So on the fill of the electrons, you can see that there are 8 bonding and 3 anti-bonding. So we've got 2, 3 anti-bonding and 2, 4, 6, 8 bonding. So if we do our bond order, we get 2.5, and that's more like a triple bond, because remember we can get fractions, than what it is to a double bond, and that agrees with our experimental data. So molecular orbital theory is a great theory for explaining the nature of nitric oxide. Okay, so let's have a go at a concept check. So sketch the molecular orbitals of H2 minus ion and draw the energy level diagram. Write the electron configuration of the ion in terms of the MOs. So we're looking at our boxes here. So calculate the bond order, and on excitation, whereby an electron's move to a higher energy, so the excited state, would you expect the excited state of H2 minus to be stable? Okay, so let's go through these. So molecular orbital theory, so we've got our 1s2 and then just our 1s1 for the negative, so that one's lost one. So we've got 2, 3. So we've got 2, 3. The bond order would be our bonding minus our anti-bonding, so we'd have a half. Okay, if we get excitation, we would have this one moving up to the next one, and then we would have 1 minus 2. Okay, so it would be unstable because the bond order wouldn't be good, because we'd have 1 minus 2, which gives us minus 1. Okay, so we get a negative value, so it wouldn't be likely. Okay, so let's have a look at another one. So explain the following. So a peroxide ion O2 minus has a longer bond than the superoxide ion O2 minus. So let's have a look at our interaction. So we know that the oxygens have a small interaction because they're more onto that right hand side of the P block. Okay, so going through that, writing it out. So small interaction means that we got our sigma and then our pi. So 2, 4, 6, 8, 10, 11, 12, 13, and so one extra would be 14 in this one. Okay, so then looking at our bond order, we would have 2, 4, 6, 8 minus 3, 5, so it'd be 1.5. And this one would be 2, 4, 6, 8 minus 2, 4, 6, so we would get 1. So this one would be the shorter bond and this would be the longer bond. Okay, so also explain the magnetic properties of B2 are consistent with the the pi 2p being lower in energy than the sigma 2p. Okay, so let's compare the small to large interactions. Okay, so we've got 2, 4, 6, or we've got 2, 4, 5, 6. Okay, so we know that B2 has the 2p being lower in energy with the the pi rather than the sigma. Okay, and that would make it paramagnetic. Oops. Okay, because we have unpaired electrons. Okay, so let's look at light and chemical detective. So we've talked about this in the lab, so I'll kind of assume a little bit of knowledge when I go through this section. So electromagnetic radiation is the way energy travels through space. Okay, so traveling through a vacuum, it behaves similar to waves traveling through water, and waves have characteristics such as frequency, wavelength, and amplitude. Okay, so wavelength is from one peak to the next peak. Frequency is the number of waves that pass per given time, so unit of time, and the amplitude is the height of your peaks from the center of if you draw a line down the center. Okay, so violet light, so purple light has a wave length of 400 nanometers. Okay, and we know that from what we've talked about in transition metals. So we had our wheel of colors. Okay, whereas infrared radiation is 800 nanometers. Okay, so we've got different wavelengths for different kinds of energy waves. And what units and formulas and stuff do we have? We have the speed of light equals the wavelength times the frequency, and this shows an inverse relationship. So the wavelength is the opposite, or has an inverse relationship to the frequency there. Okay, so let's have a look at our regions. So the ones that we're interested in is IR, radio waves, and UV. Okay, so UV, so how does UV work? So it's the electronic energies that we use to promote from the low energy state to the high energy state. Okay, so UV is that promotion of electrons, and the types of compounds that have strong interactions in this UV region are compounds that have conjugated systems or transition metals. Okay, so we can easily have that DD transition with our transition metals, or we can have the movement of electrons in the conjugated systems. So IR is our vibrational energies. Okay, so vibrational, stretching, vibrating, bending kind of energy level in there, and we'll talk a bit about IR and how that works later. And the other one that we're interested in is that kind of radio waves area, and that's our nuclear spin energy levels. Okay, so if you go this way, we're increasing our wavelength, but we're also decreasing the energy and frequency. Okay, so down this way it's more higher energy, so the UV. So let's have a look at this. So our IR is kind of like our vibrational bending, stretching, so it's enough energy to make the molecules move around. And then when you get to UV, it's enough to actually, more than move it, it actually promotes an electron from a lower energy to a higher energy. And X-rays, the reason X-rays are bad is because it actually can knock that electron completely out of the molecule. Okay, so it actually picks up charges. Okay, so as we go from radio waves or long radio waves all the way up to gamma rays, we're putting more energy into the system and we're knocking electrons off and making it a lot more dangerous. Okay, so let's have a look at our regions and our techniques. So X-rays, we pretty much all know what X-rays do. So it's good for structural determination and crystallography. We've got our UV, so invisible region, and this is our UV vis spectrometry that we use in this, and this is electronic. Okay, so this is ionizing energy, this is electronic energy, so promotion of those electrons to a higher orbital. We've got our infrared, which is our vibrational, and that's IR spectroscopy, which we used down in the lab already. Microwave is our rotational, which is Raman spectroscopy, and our radio frequencies is our nuclear spin. Okay, so getting the spin on the atoms, and that's our nuclear magnetic resonance spectroscopy, so NMR. You'll talk more about NMR when you get into advanced bioscience laboratories, if you're doing that in January. I recommend that subject if you're interested in lab work. It's really good. Okay, so Beer-Lambert's law, so we've talked about this, we've used it in our prac write-ups. So it's the intensity of the light entering a substance will be attenuated or reduced by the amount of light absorbed by the molecule. Okay, so our AO and our our I at the initial and our I final. Okay, so we can detect how much we're putting in and how much is actually being absorbed by the sample. So the ratio or percent of light intensity exiting the solution compared to the incidental intensity gives us the transmittance. Okay, and this is related to our absorbance, so we have our formulas there. So as the quantity or as our quantitative analytical technique, we need a way to relate the amount of absorption to how much of the compound is present in the sample, and this is where we come into Beer's law. Okay, so it's a linear relationship, so the number of moles in a sample is our concentration, and the absorption, so how much of it's absorbing, and we've got our path length, which is a cuvette, which is 1, and E is our molar absorption coefficient. So the higher the E value, the more effective it is at absorbing light, and the lower the concentration that can be detected. So this is a constant per particular compound. So each compound has a different epsilon or molar absorption coefficient. Okay, and we use this relationship to work out how much is in something. So we can do various concentrations and plot a standard curve, which we've done before in the lab. So UV vis, okay, so we have our light source, we have our slits, and then we've got our monochromator, we've got our sample, okay, so we choose which wavelength we want to pass through our sample, and then we see how much is actually passed through, and we detect that. And then I guess we used to use a computer like this, but now we just have our little LCD display. So we're seeing how much is actually getting through that sample. Okay, so we have a solution of 4-aminobenzoic acid, gives a maximum absorbance of 0.49. What is the percent transmittance? Okay, this is our graph that we get. So the absorbance equals 2 minus log percent transmittance. So the percent transmittance equals 10 to the 2 minus the absorbance. Okay, so that would be 33%. Pardon me. Okay, so the absorption spectra shown below of the solution of naphthalene in hexane obtained through the path length of 1 centimeter. What is the concentration of the sample? So then we know Beer's law, so absorbance equals ECl. We're given our E, we need to find our C, and we can work out our absorbance, reading off the graph, 0.49. Okay, it's pretty straightforward. Okay, so let's look at infrared spectroscopy. So like I said, this is our vibrational spectroscopy. So one way of visualizing it is that you have your 2 atoms and they're balls, and they're connected by a spring between them. So the movement of those 2 balls on the spring can show you the different types of vibrations that you will get. So in the ground state, you will get small vibrations, so stretching and bending the spring, and as atoms absorb the energy, the range of these vibrations increase. So not all vibrations are absorbed in IR. There needs to be a dipole between the 2 atoms for there to be an absorption. Okay, so the amount of absorption is related to the type of atoms in the bond. So strong polar bonds absorb more energy, and symmetrical bonds are considered IR inactive since there is no dipole when applied across the field. So basically what we can see using our infrared spectroscopy is that you will get these regions. Okay, so this is what the pictures look like. We've looked at these already. So you'll get these regions and they correlate to functional groups. So if we have a peak around about 3,200, that correlates to an OH group. If we have something just below 3,000, that's our CH stretching. And we can say, okay, well this molecule has an OH and a CH region. And this is our fingerprint region. So it's complicated and you can't really pick out key characteristics from this region. So this is our correlation tables. So our OH and our carbonyl are the most common ones that we kind of pick up. NHs are quite good to find out, and CNs. Okay, so what you will be given is a correlation picture or a statement, and you'll need to work out which functional group that correlates to. So let's look at these ones. So here we have a nice sharp peak around, what have we got, 17, 18, so that's our carbonyl. Okay, and here again we've got a peak there, so another carbonyl in this molecule, and we've got an NH. Okay, and the NH is quite broad because we have the ability to hydrogen bond with any kind of water that's there. Okay, so we can see our carbon on our NH region. Okay, so let's do a concept check. So this is the type of questions you might get. So which of the following compounds would be likely to give the following IR spectrum? Okay, so looking at your correlation tables, you can see there's a carbonyl peak in there. So which of these molecules have a carbonyl? Okay, and then is there an OH? No, there's not an OH region there. There's nothing around here. So it's got a carbonyl with no OH. Okay, with D. Alright, and mass spec and NMR you'll do when you get to ABL. So mass spec is your mass to charge ratio. So pretty much we've got one upstairs. So you put a molecule in the mass spec instrument, and it charges the molecule and breaks it apart, and it will deflect within a magnetic environment based on the charge of the ions that are produced, and you can work out a mass to charge ratio. So NMR allows you to see the different types of, depending what sort of NMR you're doing. If you're doing proton NMR, you'll see the different types of protons. If you do carbon NMR, you'll see the different types of carbon environments within a particular molecule, and you can use this to work out what the molecule is. So NMR is the most comprehensive, and mass spec is used as a kind of quick kind of analysis type thing. And to fully characterize a particular compound, you need an NMR, a mass spec, and an IR in combination to say that that's the particular compound that you've got, if the compound has not been made before, so if it's a novel compound. Okay, so you'll do similar problems like this in ABL. So you'll be given an IR spectrum, you look at it and you go, okay, that's a carbonyl peak in that molecule, and then you'll be given a mass spec, and you'll say, okay, well that's the mass of that particular, you'll be giving the formula, and you need to work out what that actual compound is. You'll be given the mass of that compound. Okay, so you'll be given the mass of that compound. You will look at it and you'll go C5H10O2. Okay, what sort of things can break apart of it? You can see, okay, we've got a CH2CH3 that's broken off because it correlates to 29. You've got a 16. You've got a loss of another 12. So you can see what sort of molecules that are fractions that are breaking apart. And you'll have your proton spectra. This is what one looks like. So this is an OCH3 peak. This is a carbonyl CH3, okay, because they're quite high. So the higher they are to the left, so the higher the number, the more electronegative the thing is that's next to it. Okay, and you'll get your carbon spectra, and you piece all the bits to the puzzle and you work it out. Okay, so I won't go into it in too much detail, but all the pieces of the puzzle go together to give you your compound. Cool. So thank you very much for listening. Hopefully I covered enough of everything for you, and I will put up some revision stuff for you. So have a go at the practice exam, have a go at the revision resources that are there, and thank you for such a great semester. Bye.